We're recording. Okay, great. Go ahead and share. Let's see. Every time you share a PowerPoint, things get wonky. That's not fun. One of my screens decided to die on me, so I'm trying to figure out how to make this happy. Let's see. Which view are you all getting right now?
We see the not the audience view, but the presenter.
Presenter view.
There,
yeah.
that's the
There,
full
that's it.
screen.
That's it.
I did the thing. Okay.
Right.
Thanks, everyone. All right. Well, welcome all to our PyHC Fall 2022 meeting. I'm just giving a couple quick slides that a lot of you have seen before, but there are a couple new people. So let's see. So PyHC, just a wildly fast intro. So yeah, we're community knowledge base for performing heliophysics research in Python. The goal of our effort as a community is to help establish standards and processes, share lessons learned among developers herein, try to reduce the incident of duplicated efforts, find opportunities for future collaboration amongst each other, and ensure that existing software tools are interoperable. Someone's mic is unmuted, by the way.
He's not muted.
All right.
Let's see, mute. I'm just gonna start muting people. Okay, in any case, so twice yearly, PyHC is supposed to meet in person, but with the pandemic and everything, it's been, not quite that for the last couple of years, but hopefully in the spring, that's what I'm aiming for. We also have, in general, biweekly telecons that we have as schedules allow and meetings allow and holidays and so forth. And there are a couple other meetings that we always participate in, including the yearly AGU meeting, which we will have both poster session and an oral session this year for the first time at the AGU 2022 meeting. So be on the lookout for that. Information about that should be on our website. It may need to be updated with the exact dates and times, but that'll be up there soon. And as of this year, we started holding a summer school. So this is our 9th PyHC meeting, and it's our 6th all virtual meeting. The pandemic continues. But as has been the case for past meetings that we've done virtually, all meeting days are going to run 9 to 11 on Zoom and to be covered during this meeting. So today we have a bunch of project updates and some bigger initiative overviews. Yeah, sorry, this is the slide from last time. But then tomorrow is just going to be some more updates, project updates, various talks and so forth, some discussion times. Wednesday, we're going to have both a tutorial and a hackathon session. And then Thursday, we'll hear a little bit about the hackathon session and have some more discussion period. So just a few meeting housekeeping and notes. If you're not presenting, keep yourself muted, please. All documents and presentation associated with this meeting are going to be on our PyHC D drive. The links for that you can find on the meetings webpage. And if you're presenting today, please remember to send me your slides. We also have a general conference notes document. I will put a link for that in the chat. And as I mentioned before, this is being recorded. So if you don't want your lovely face seen when you're talking, just make sure to turn your camera off. And that is all I have for intro. So let's see.
Yeah, could I pop in for a second?
Yeah, go ahead, John.
Yeah, for anyone who's been out of the loop on PyHC communications, we have a Slack channel now. I'm going to paste an invite link into the chat right now, actually. Boom, there it is. Feel free to join this Slack space to follow along or talk about anything that we talk about during the meeting. We only use the general channel, and what's fun about it is that channel is linked with our Element chat room. So every message that shows up in one room will show up in the other. So if you liked Element better, you can keep using that one. But yeah, I encourage people to use it.
I would explain why Element is suddenly active.
Element is suddenly very active now. That happened.
Wonderful. Thanks, Sean.
You're welcome. Rebecca says I get a glitch.
Interesting.
Anyone else confirm or deny that the link does something?
Mine makes Slack pop up.
Yep, I just copied it right out the app. Cool.
Okay. NASA
Right.
VPN.
Well, I don't know if I had anything else other than that, just encouraging people to use it.
I'm getting a million notifications for people joining the space, so.
Oh, nice.
It-
We can just you can disable that. I
No,
think.
I was gonna say your PSA did its work.
Awesome.
All right, cool. Thanks, Sean. Let's see. So first up, as far as package overviews and intros go, we have a Happy overview. And Happy recently joined us actually as a core package in PyHC, if you all weren't aware. So
Oh, I'm seeing Doug Lindholm's name on this presentation. He helped out with this.
Yeah, he's been participating in some of the discussions recently. So, and he's been involved with it for a long time. So
That's awesome. I mean, I talk to him every day at work, and he's told me he's been participating. I didn't know he helped put together a talk or anything deeper than just.
well, this is
there.
when I present on behalf of the Happy team. So
That's very nice.
yeah. So yeah, I'll present an update today, what we've got going. I'll got some stuff at the beginning to describe what is Happy in case it's new. And then at the end, some stuff about what's new in version 3.1. So let's see, there we go. We've got our logo in place, but in case you didn't know, here's the definition, the heliophysics application programmers interface, Happy. And the fundamentally Happy is a specification, a language independent definition. It's web-based, so it's request and response standard for getting data. And Happy servers implement the specification and allow you to get data. And then Happy clients are things that run on your computer and go ahead and get data. So the agenda today will start at 20,000 feet, Happy's place in the HDRL, which is the Heliophysics Digital Resource Library. We'll start zooming in a little bit, Happy's role in PyHC, and then ground level details with some of our new features and plans. So the HDRL, if you don't know, is kind of what we're calling the heliophysics data environment right now. It's been pitched to headquarters that way. Aaron can jump in if he wants to say any more about that. But the foundation is sort of the data policy. Here's what we're expecting to happen for data. On top of that, of course, are all the standards mentioned and endorsed or enforced by the policy. And then the main archives and their associated services that, leverage those standards and make data and services available. And then there's a whole bunch of other stuff that is kind of, other efforts that are going on to support the HDRL and the data environment. And, PyHC is in there, and there's support for IDEA, an international group, and SPACE, of course. And then I'm lumping Happy in there with some of these other initiatives. It's something that's been growing and trying to build on some of the standards and build ways to help support and bolster and maybe extend in some cases what some of the archives are doing.
It's this other stuff that's motivated the idea of a digital resource library instead of just a data system.
Right. Okay. And so Happy's role then is to focus on this interoperable data access. And again, since the beginning, Happy's focused on time series data. And our idea was we noticed a lot of different providers had a very similar approach. Can we distill that down to a common one, a standard one, and provide a pathway to providers to implement that? And wouldn't it be great if everybody had the same one, right? That would be kind of the idealistic goal, if there was a single API that you could reach practically everything. So that's kind of what motivates us. So how do we provide the simplified access? Well, okay, there's data from providers and users, and the internet allowed data providers to create data interfaces, ways that computer code could request data. And so you could write software to do that. What Happy is suggesting is that you don't get rid of that, but you keep it there, but now you make space for a standard mechanism, and then the software that you write to access the data from that standard can then apply to other providers as well. And the basic idea is that the standard interface is something everybody could support, the lowest common denominator. So happy requests are extremely simple. Data set name, start time, and end time. That's all you need. And then you can optionally say, well, I only want a few of the parameters. I don't need everything, just maybe one or two. So optional list of parameters. Info responses are also basic. We just the minimal amount of metadata, and it's done in JSON. And the data response is just a stream of the numbers in comma separated values. You can optionally output JSON and binary. So here is a happy request. You use the data endpoint and you give it the data set name, the start time, and the end time, and that's it. So, and then here's the result, a time followed by the columns. So now zooming in a little bit, 1,000-foot level, Happy's role in PyHC. So as Julie mentioned, Happy is now a core PyHC package, the Python client. And of course, all of our activities are open to PyHC or anyone. We have a lot of things going on. There are 27 different repos in our GitHub location. We have a weekly developers meeting. We have a roughly monthly Happy Community Forum, not every single month, but and we've had some very interesting discussions there recently. And there are email forums you can sign up for. Here's the info page. I'm not going to go over this, but this has all the links on it if you go to look back at this talk. We have a paper that Bob Weigel authored this year about the standard. And then there's some other links here to get to the different projects. Okay, I want to spend a minute talking about the Python. This is the Python meeting, so the Python client. And just to show you how simple it is, the highlighted regions show, okay, you're importing some code from the Happy Python client library. You have a few definitions of where you want to get the data. That's the server name, data set name, start and stop. And then here's this list of parameters. Then you make this single call down here, and that's goes and grabs the data. So it's really that simple. And once you get this set up for one data set, finding out other ones or adding other ones, it's very, very easy. So this is why we're excited about this as a kind of standard approach. To learn how to use the client in more detail, and there's plenty of examples, worked out examples, there's a really nice tutorial that was developed as a part of the well-attended and now famous PyHC summer school. And so there's Jupyter notebooks and video recordings from that. And you can follow through those on your own and really come up to speed. Probably in like an afternoon or so, you can could get to a good point with being able to use it. Okay, there's other elements in the Happy ecosystem besides the Python pieces. I've highlighted the Python ones here, but there are other data servers. There is a generic Python server. We haven't talked too much about that here, but that's got plugins. If you want to serve your own data, there's places you can hook in to serve your data through Happy. There's a Node.js server and a generic Java server that's been developed in conjunction with some efforts at ESAC, the European Data Center. And of course, talked about the Happy Python client. There's PySpeedas, which is another Python mechanism for getting Happy data. I think it also now uses the Happy Python client. And a couple other things to mention. There's a Happy verifier. If you want to develop your own server, you should run it through this verifier mechanism, and it'll tell you if your server is meeting all of the requirements of the specification, and it lights up yellow, green, red if there are any issues. And it can deeply check every single thing that your server is offering. It's very nice. And then there's this web portal for exploring known public Happy servers. That's actually very useful. Even during analysis, you can see what data is available quickly there. So that's something to keep in mind. All right, ground level details, including updates for version 3.1. We have a couple of really nice new features, including additional metadata, and then being able to identify coordinate system and vector quantities. The only thing I'll say about this last one, servers can now advertise if a time range is, what the maximum time range is for a data set. Before, you had to just submit a request would give you an error. Oh, that's too big. Now servers can advertise, hey, here's the max you could ever request. Anything bigger than that will give you an error. Okay, so about the additional metadata, you've always been able to do this, but it was a little bit awkward. You had to prefix any additional metadata keywords with X underscore so they wouldn't collide. But now you could just stuff an entire block of additional metadata in so that it won't collide. And that preservation, that'll help preserve metadata as you transition data from one data model to another. At least we're not losing any metadata. So here's an example of that. You'd have this additional metadata block, and inside that is a list of other metadata items. You can either refer to it by reference, like with the content URL here, or you can stuff the actual content in there as well, just as keyword value pairs, depending on how you want to do that. Or you, like for the fits, you could stuff in fits keywords, and then if you have ISTP keywords or something from a CDF file, you could put those in as well as key value pairs. And then coordinate systems. This was something that's been requested, but it's can get really complicated fast. So we try to come up with something simple that would allow most data to be described accurately. So the data set can specify a coordinate system schema. I'm not showing that on the example below here, but the schema is a computer readable list of all the coordinate system names that you're going to allow in your data. And then within the parameters where you describe each parameter, you can refer to the coordinate system names from that schema. And so here's an example where you have a spacecraft location, the coordinate system name is GSM, and then the vector components, well, it's a 3 vector. You can see the size of 3 there. And then the vector components are X, Y, and Z. If you have non-Cartesian, you can describe that too. Maybe you have magnetic local time and latitude. You can describe it with different vector components. And there's a enumeration of all the allowed vector components. And we've captured everything, I think, that mathematically can be a component for a directed or directional or vector quantity. Okay, future plans. We've been talking with some folks from the Netherlands. They found a way to link different data sets that differ only by the cadence. So as you zoom in, you can start getting finer time resolutions on your plots. We're going to find a way to do that easily with a few keywords. I'm not going to read all of these. I'll just focus on the highlighted ones. We need to figure out ways to do federated happy server lists. Right now, it's a very, very basic way, and it requires us to edit a list in GitHub. So we need to have a better way of discovering which different happy servers are out there. We're definitely going to pursue more ground-based data providers. And then we have the spec itself is in a GitHub repo, and there are a lot of issues on there, things that we realize, well, we should talk about this and figure it out at some point. So that's what our weekly meeting is, going through stuff like that. Okay, I'll quickly go over this. There are a lot of different data sets available with Happy. NASA, and then some in Europe. LASP has some of their solar irradiance data. The Swarm mission picked this up. The DOS2 server at Iowa also talks Happy. We're working on one for ESA, and that's imminent. We've been working on one for a while for SuperMag and some timed Groovy data. We just keep bumping into strange issues there, but that's still in progress. And we were recently contacted by the Royal Netherlands Meteorological Institute, and they're using it for a space weather portal. We're still hoping to get the PDS PPI node to get their data in there, and I'm going to be pursuing the Madrigal folks for some ground-based stuff soon. And then I think I'm okay on time. I have maybe a minute left. I'll zoom back out briefly on this. Using Happy actually has implications back on the data providers. If there are certain things that Happy allows or doesn't allow, that's actually kind of sort of intended to push back on data providers. A lot of people have asked us, oh, well, my data set has all these different settings for background subtraction levels or different options, and Happy doesn't allow you to specify those options. So Happy is only for fully finalized data products, and that's I think, a good thing because it's encouraging people get your data ready to be analyzed without having to make lots of choices. Now, some choices are inevitable, but if the combinatorics gets really big, then actually it makes your data harder to analyze. So the other thing, Happy doesn't allow for passwords or user registrations. This is part of NASA's open science push. We realize sometimes that is necessary, but it probably needs to be managed outside of Happy itself. Yeah, like all other security concerns, you can manage that in a different way, and we don't need to commingle that with the spec. Units and coordinate systems, there's just all over the map. We're really hoping that Happy will provide pressure for people to standardize, especially on coordinate systems. There are some good unit schemas out there. And then this idea of longevity and durability. If data is easily accessible with Happy, people may expect it to be there long term, especially if you want to reference a DOI with some of the stuff that you used for a paper. And then last slide here, interoperability lessons. The best way, this is possibly contentious, but I think the best way to enable programmatic access for a lot of diverse resources is not to map everything to everything, but to map between a small set of existing standards. We've kind of done this for formats, and now we're doing it for services. And so if you have community code that's some kind of a reusable library, generally it's a large set of library routines, and then at the application layer, a small set of example routines. And if you have individual code, people can build their own libraries, and they certainly do, but a lot of times individual code is more at the application level. And so the example routines are what you copy, paste, modify to get into your own code, but the reader library is what you should fully reuse with no changes. And this is the kind of approach I think PyHC can try to encourage with new sort of interoperable mechanisms that are being proposed. So that's, oh, and tomorrow we have a whole hour to talk about this. There's an adapters project that Sandy, Jeremy, and John have been working on, and they're going to talk about that. So stay tuned for that one. And that's it from me.
Thanks, John. You have a couple questions in the chat. We can hit some of them up.
Oh, haven't been monitoring the chat. Let me see.
That's okay. Sean had asked, what does that time range advertisement look like?
Yeah, I've only seen getting the time range from an info request. I don't know that I've seen the new version.
Yeah, you can specify a max time range for each data set. There's just another optional keyword in the info response. And it just gives you a ISO duration that tells you this is the, this is your max time range for this data set.
But is it still the case that I have to make an info request with that data set ID to get the time range?
Yes.
Oh, okay. Sorry. I thought you were saying it was like available more upfront somehow. Never mind.
Right. No, you still have to get the info request to find out about that data set. Yeah.
Okay. Next question.
Let's see. Yeah. Talk to Alec Engel about cloud to cloud data reading. Yeah. And we have a cloud project working on that too. We just haven't fused Happy into that.
They're looking at a way to speed it up. That's why I was
Right,
recommending the connection.
Yeah. Yeah. Okay. Yeah. There's different cloud optimized data formats. And so.
Well, it wasn't about data format. It was about the actual transmission of data outside of the formats. Beyond that, I honestly don't understand what he was talking about, but you'll have to contact him.
Okay. Yeah. See if he's got any published results on that. Sandy did publish a paper on the timings it takes to read various formats in the cloud, whether they're cloud optimized or not. So that just got published a few weeks ago.
In the PyHC Special Frontiers issue.
Komodo has a Madrigal portal. Okay, that would be good. Yeah, I haven't talked to Madrigal folks at all other than, hey, would you be interested in this? And they said, definitely yes. And that was at CEDAR in the summer, and I haven't really followed up yet.
It looks like Ryan's question got answered by Sandy.
Okay.
But Jack, you have your hand up. Let's get your question.
Yes, so I'd like to understand a little bit more about the Happy and images. It seems like I'm looking at an issue on GitHub Happy server, And it looks pretty close to, I mean, what we do in the VSO is most queries are, specify an instrument and then a time range. So that seems pretty close to what
Right.
Happy does. But we don't do any streaming or subsetting or anything like that. And you do get a list of URLs back, not, not the data itself. So I wonder if there's what the, should there be any, how far Happy should expand into images if it, would sort of spoil what you're working on right now, if it, if it's putting a square peg in a round hole.
Yeah, we've talked about serving images before, but and the conclusion was, well, images there are already readers for images. When you get an image, you know what to do with it. So the time series data came in so many different ways. It was there, that just wasn't the case. But what we have talked about is what you've described, returning a list of URLs. Here are the images that meet your search criteria. And so that's just a slippery slope, because then if people do that for their data files, oh, here's a list of my CDF files. Now I have a Happy server. It's like, well, that's not really what we wanted for time series data. But for images, that could actually work. So there's the person at the Netherlands Meteorological Institute. He actually did that. And he has a very nice client that he showed us at a couple of our discussions, where he was doing exactly that. So we're going to pursue that. But then wavelength and energy, yeah, that's often part of your query, right? We don't have that. So
yeah. Next time you're talking to this person, let me know. I'll be interested to see what's
Okay.
going on. Right.
Okay.
Thank you.
Great.
sure.
Thanks, John. We should probably move on to our next presentation. If you have any more questions regarding Happy and so forth, feel free to put them in the chat. So next up, we have a quick Komodo overview, recent updates, things going on from Rebecca.
Hey, trying to find the share button on Zoom, which would be where? Help me out here. Oh, there. Wow, it is Monday. Okay. Here we go. All right, so I'm giving a quick update. I wasn't originally planning on presenting, but we had some huge redesign effort going on. Nearing completion, so I'm going to give a quick update for the PyHC community. A couple of these slides, most of you will recognize. I'm just going over it with the broad strokes to introduce everyone who doesn't know what Komodo is to what it is before I say about the update, similar to John's presentation. The two QR codes you see here are to the two GitHubs. So the interesting thing about Komodo is that we're split into two GitHubs, one managed by Ensemble, our commercial partners, which manages all of the core capabilities that I'll show early in the presentation. And then the one on the right is managed by us at CCMC. And we apply the core capabilities of Komodo to heliophysics model outputs. Okay. So this is the general situation at CCMC. We have a large variety of models across all of the domains that you see here color-coded. And what we serve is not only the custom model runs and all of these specific services on top of the models. We also have services related to model validations, forecasting, these different things, and all of these scoreboards and validation efforts. We're also pursuing offering Komodo on top of these observations, and that's what I'm talking about today. Okay, so what is Komodo? Komodo is a way to apply the idea of data functionalization on top of any data set. So this isn't specifically related to heliophysics in its original design, or even in its current design. We're just applying that on top of heliophysics data at CCMC. So what do I mean by data functionalization? Basically, applying an interpolator on top of your data set. And in Komodo, that enables a lot of basic capabilities, such as unit conversions, that you see here with some simple syntax, function composition, interpolation, of course, as you see here, and some really nice interactive plotting through Plotly that the video is showing you with all the zoom and features, and you can save the interactive quality. What we're doing at CCMC The first level is what we call model readers, and this is basically a model agnostic interface to all of the model specific things that these model outputs offer. What you see here on the top right is a list of the models currently coming in the next update, coming soon, preferably before Thanksgiving. And then the power here that we're using Komodo to do is that we're offering, for the first time, functionalized data access without having to know all of the model specific things, like what coordinate grid is it on? What data format is this in, right? Think of this as the precursor of happy for model outputs, right? So instead of JSON, we're doing functionalization. Of course, we are looking towards adding happy on top of this, not quite there yet. But the interesting thing is here is like you have 2-3 lines of code and you suddenly have functionalized access to CTP data. Same thing for GitHub. Notice the syntax change is only the model name changed and where the data is located is changed, of course. Please keep your model data in different files or you will make it go crazy. Okay, but another cool thing is that this particular temperature, neutral temperature variable in the CTP model depends on pressure level. So the model reader automatically knows to pull in all of this other information, invert the pressure level grid, and then offer you a temperature, a neutral temperature function that depends on height, and of course the original one if you want to play with that. That's not the case with GitHub. The GitHub's neutral temperature function depends directly on the height grid, but the user did not have to know that. It takes care of all of these details behind the scenes. Okay, once you have the data functionalized with the model reader for different models, you can pull these into the same Komodo object here, and then very quickly plot what all of these models simulate for the same event with a few lines of code. So this is just slicing through a 4-dimensional data set to give you a 1-dimensional plot for each one. Notice WacomX is in here. Kind of proud of that one. Okay, so built on top of these model readers is the satellite fly-through. We have a couple different options I'll show in the next slide, but the basic idea is that any coordinate conversions that you want are handled all behind the scenes. You tell it what coordinate, sorry, I keep forgetting this is not a notebook, it's a screenshot. You tell it what coordinate system you want and it takes care of everything else behind the scenes. In this case, CTP and GitHub are on the same coordinate system, but you don't have to know that. Once that data is functionalized, you can pull in some observational data through happy, that we've done the same thing, just do the happy commands and then functionalize it with this cool little function. And now you can do function composition to do some basic ensemble modeling calculations and then compare that ensemble model, oops, sorry, this one, compare the ensemble model to the data with the same interactivity as before. Okay, we have a couple different options for trajectories. What I showed on the previous slide was for real flight, which took a real satellite trajectory and flew it through the data. That's offered through SSE Web. And then TLE flight is new. That's why it's red. You can give it a file of 2-line elements and it'll convert it into a trajectory using the SGB4 propagator, which is the standard. There's flake flight, which you can use to generate a play trajectory to see if you're sane that day or just something to play with to make sure you to play with it. And then you can use model fly through or my flight to build your own satellite trajectory. The video that you saw here is a sample of the interactive plots that you can generate through the fly through using our specialized customizations. Okay, I'm going to focus here on what's new. The model readers are closing up a complete redesign. What's new here is that the model readers automatically functionalize the entire data set in the directory instead of a single file. And there's multiple lazy interpolation schemes. Of course, you can't read in the entire model run for GitHub over 2 months. So in order to functionalize the entire directory, we use lazy interpolation. And there's a couple different options which depend upon the data format underneath, the data structure. So if you plan on developing one, come talk to me on Wednesday or Thursday, whatever day the hackathon is. All right, so I'm not going to read all this. You can read it here, but the previous standard is to functionalize the entire data set at once. And there's a couple of new, much faster ways to do it, particularly for larger data sets, including WacomX, if you've ever played with that. The logic is streamlined for fast execution. We have now a faster and more accurate and generalized pressure level inversion to take care of those models that have that. And we now have a built-in structure for custom interpolation routines, which will make our collaborations with the Gamera team and the Marble modeling team to a much smoother process. Okay, we have more models coming in the next release. The new ones are SuperDarn, WacomX, WhereMyPE, and DTM. These are ones we've had before. This one we had before, but now it's going to be a lot faster. Sorry, let me cancel my timer. These are the ones we're working on next, and that's my presentation.
Thanks so much, Rebecca. Do we have a quick question or two for Rebecca? Pete, go ahead.
We can't hear you, Pete, if you're talking.
Sorry, no mic. Okay, go ahead and put it into the chat. But John, go ahead with your question.
You're
There.
muted.
Yeah. So
Yeah.
on page 5, you had you're consulting different models with the same kind of input. Do you have a mechanism for, hey, if models take the same kind of input, you can kind of treat them all the same, or
That's exactly the point. That's how we're designing it.
Okay, so can you go back and show page 5 again? I think it was page 5.
I have to reshare. Hold on.
Oh.
Find the green button. That's fine. Where this? Okay. I'm just gonna do this. It's not finding it. I'm sorry. Hold on just a moment.
Well, the concept is just that if you have a model, a whole class of models that have the same exact kind of query structure, then you could start to treat them all as almost like as a physical model, not just a computer science model. I don't know if that's making sense. We've talked about this as the next layer on top of HAPI. We called it science data interfaces. You would say, okay, not only is this a HAPI resource, but this is a magnetic field. And then there would be ways to know, oh, well, if it's magnetic field, then this parameter has a certain identity as the magnetic field vector, and and so forth. Maybe it was the next page. Yeah, that was it. Oh, it
Like
was
this? Too far?
no. It was when you're on page 5 and then you clicked next, it showed a different
The second overlay on page 5.
yeah.
This?
One
Just
more.
One more, so third overlay.
There, that. Okay, yeah.
Okay.
See how the plot underscore partial has the same thing every time. So that's. Can you characterize that as this is a certain kind of model? And come up
This
with
doesn't care what data is underneath it. Notice right here, the user chose the name and chose the units. Any unit conversion that needed to happen happened here automatically. And now that we're plotting this, these are just referencing the names that the user chose. These are referencing the names of the coordinate grids that were assigned in the model reader. In this case, they happen to be the same.
Okay, well, we can take this offline. This is where the in-person would be fun because we could continue this in the hall. But you're
Sounds
not
great.
that far
Maybe in the
away, so
spring.
we could do that sometime. Yeah.
Okay.
Spring. Look forward to the spring.
Should I stop sharing?
Yeah.
Okay, go ahead. Should be good now. Let me know.
Yeah, I think Pete put his question in the chat. We should probably move on to the next presentation, but it's there for reviewing, Rebecca.
Thanks.
All right. So next up, we have a quick overview of a newer project to all of us called Last Packets. Gavin, you here? I see you.
Yes,
Yeah.
hello.
Hi.
All right, let's see. I think I have, I'm taking a risk here. I'm going to do a live demo. We'll see how this goes. Let's see. Okay, I'm going to start with some slides. We'll see if that goes. Okay. So, hi. Oh, whoops.
Yep, we're seeing presenter view.
You're seeing presenter view. Interesting. Okay. Yeah, that's okay. As long as you guys don't mind, I don't mind.
I
I'd rather
think the
save the
swap
time.
displays button up in the top left would do what you want.
Oh yeah, let's try that. How's that look?
Boom.
Looks great.
Amazing. Thank you, Sean. I think that was Sean. All
I
right.
got you, Gavin.
Hi, I'm Gavin Medley. I work on the data systems team, specifically in science data processing at last. Basically, I write software that, wow, I just realized that dummy text in my presentation. Sorry about that. I basically write science data processing software that turns the raw downlinked L0 data from our instruments into usable science data products that our science team uses to actually publish data, to publish their papers. So I do a lot of work with the raw data. I do a lot of work with metadata. And I noticed that there was kind of a lack in terms of reusable code within our organization and in the community as a whole in terms of being able to decode our L0 data in a generic way. And this is a lack that's been identified by several different parties. So there are multiple solutions out there to this at the moment. And it's, you know, they kind of approach the problem slightly differently. I'm going to talk about my solution that I'm kind of publicizing. Basically, CCSDS, for those who don't know, is the Consultative Committee on Space Data Systems. They have defined the format, the binary format of the telemetry packets that we bring down from our instruments. This is what we typically call L0 data. This is not very accessible once it actually is archived. In fact, most people never even look at it. And that's partly because it's binary encoded and it's not very user-friendly, that's why I have my job, right? As I turn these this L0 data into research products. So we decode this data though for every single mission. So every science data processing pipeline that we write, or pretty much anyone writes, uses the CCSDS packets, and usually it's a hard-coded definition with purpose-built code for decoding these packets into actual usable engineering values, which are then calibrated and geolocated. That definition, I'll just put the URL in the PowerPoint presentation, but essentially it's this format. So you get a primary header, and then the rest of it is the packet data field. And the primary header is very consistent. It's perfectly consistent in terms of its data format across every single telemetry packet we ever receive. Secondary header is optional. It can be lots of different things. User data field is totally flexible. It could, in theory, just be a giant binary blob, or it could be interrelated fields. There could be a lot of complexity in that data field. And so there's a difficulty in defining the fundamental structure of these packets for decoding. This is what XTCE, where XTCE comes in. XTCE is another standard developed by the CCSDS. It's an XML format that defines the structure of these packets. And it defines a schema that allows you to define very flexible definitions that can all be interpreted in a consistent way. The lack there, though, was there's not really very much software outside of command and control systems like Cosmos that actually can decode these packets very easily. At least nothing that I could find, certainly nothing open source. It supports things like inheritance of packet structures, dynamic decoding, determination of packet structures based on app ID, and they have a whole green book for this XML format. So I created a Python library that reads an XTCE XML definition, creates an object representation of that definition, complete with evaluate methods, so that you can dynamically evaluate the full, or basically decode the entire packet structures serially. Then it reads a binary packets file of concatenated packets and iterates through those packets, decoding each one dynamically and spitting out possibly even calibrated values. So it decodes the raw value, the name of the value, and potentially can do things like interpolation or enum lookup, things like that for each value. So it works pretty well. Mixed app IDs are okay. So we call it a decommutator as well as a decoder, but that requires that the definition going into it is comprehensive. It's pretty fast, but it's really dependent on packet complexity. So if you have a lot of fields in your packet that are dynamic, especially strings, it can get kind of slow. And obviously any conversions or transformations that are introduced in the XDCE structure also slow it down. But memory usage is entirely dependent on how the user uses it. So we provide a generator that generates packets. So it only ever one packet is in memory at a time. But if you concatenate all of that into a list, obviously you can use a lot of memory. Okay, that's the end of my slides. I just wanted to give a brief overview on that stuff. And now I want to show you the library. So let's see, that's not it. This is it. So for those familiar with Python, maybe this will look familiar. Essentially, we provide.
Sorry, Gavin.
Yeah.
You could do with a zoom in or two, please.
Thank you. Yes. And I'm sorry that I'm going fast. I'm just aware that there is a time crunch here. Font. Okay, how's that?
Beautiful.
Okay, so let me collapse all of this. So we have a hard-coded header definition. As I mentioned, that's something that is always going to be there. It's always going to be the same set of formats, and we provide pre-named fields for those, but you can actually rename them if you need to. And then we have this packet parser class. You essentially instantiate this with a definition read from an XDCE document, and then use this to parse binary constant bit streams that are read from L0 files. So this parse packet returns a generator object, the generator returns packet objects iteratively, and every single packet gets decoded based on the entire XDC definition. And that XDC definition is stored in memory. So you only have to read that once, and then you can decode literally millions of packets in a few minutes if you need to. I'm not going to go too deep into this code, but this is kind of the structure of it. It's very simple. It has one dependency on this bit string library. We keep NumPy out of it. We keep everything out of it, basically, so that the user can decide what they want to do with those raw packets. The entire purpose of this is only to interpret XDCE and dynamically decode your packets. Okay, I don't want to go too deep into the code. There's not too much to show there, but I want to show an example of how this works. So what I have here in AWS is an object Lambda access point. Essentially, I've set this up so that we have a bucket of CCSDS packet data. This is a binary file with concatenated L0 packets from, I think it's from JPSS1. And then we have an XDCE definition that looks like this. So this is kind of what an XDCE definition looks like. Most of you probably won't have to deal with this ever, but essentially this completely defines all of the different packet types that we maybe will encounter in this file, all of their types, their ordering, the number of bits, the way to interpret them, whether they're signed or unsigned integers, all of that information and that might need to be used to decode their values, including short descriptions of them. So we have our definition in one bucket, we have the data in another, and I have a Lambda function set up so that if I access it through this object Lambda access point, it will dynamically decommutate these packets into a CSV file. And this worked a few minutes ago. It's going to take a few seconds because it's a lot of packets. It's 2 hours of, I think, 10 hertz packet data for geolocation. So you can do the math on how many million or how many hundreds of thousands of packets that is. But we just decoded all of those binary data values into real values, including a CSV header that came out with the names defined in the XDCE document. That's kind of the end of my demo. If this is of interest to anybody, I think really this will mostly be of interest to people who actually do the data processing and software engineering for this. This library has been used, it's being used on Libera. I believe Clario is using it, and I think CubeSats are also using this to decommutate some of their packet streams. If anyone has any questions, feel free to let me know. I'm happy to answer. Oh, and one last thing. This is available on PyPy if you want to install it. It's last packets 2.1. There's a relatively useful, oh, actually, you know what? If you need help using it, get in contact with me. I just realized the README will not be in the built distribution. So if you need the README and some examples, feel free to reach out. My email address is gavin.medley@lasp.colorado.edu, and I'll put that in the chat.
Thanks, Kevin. Quick question or comment from anyone in the crowd before we move on? John, what missions have you used last packets on? I think you mentioned that one.
Yeah, good question. So it's being used on Libera, but Libera hasn't launched yet. So, you know, it's not exactly in the wild. It's also being used on Clario, which also hasn't launched yet, but it's very close to launch. So I think that pipeline is pretty mature. I know it's being used on CubeSats that actually are already flying. I'm not sure if they're using XTCE, or some of you may have noticed there's also a little bit of functionality for a CSV-based definition. It's possible that they're using the CSV-based definition. The parsing and all of that is exactly the same. The only difference there is where the definition of the packets comes from. And while the CSV stuff works, it's very rudimentary. It's not super well tested, and I don't think it's quite as much. It's not certainly not as mature as the XTCE-based stuff.
Okay, thanks. Yeah, no, that's great. I mean, it's got heritage though, right? You're fleshing it out with several different missions.
I mean, you know, I really didn't do a lot of thinking when I implemented this, to be honest. This entire standard was created by CCSDS. Like, I just implemented their standard and made a parsing library for it. There's nothing very fancy in here. In fact, all of the logic that I implemented is already defined in this XTCE spec. So I didn't really add anything to this. I just made a parsing library that for some reason no one else made. Or actually, having said that, it definitely exists somewhere else. It exists within Cosmos, the command and control software, but I don't know how to access that code. And I don't know, like, you know, I figured I'd make something that's a little more open source.
Yeah, great.
Thanks. One last question from Jack.
I might have missed it. Is this publicly available somewhere? The not for download, like, is there a GitHub repository or anything?
So there is a Bitbucket repository. It currently resides within LASP, so it is not publicly available, but it's Python code. So the code is in the built artifact that's available on PyPy if you want to go look at it. I actually submitted a PDART proposal this spring. It was rejected with the primary criticism being that the library didn't already exist. The library mostly did exist at that point. I just didn't write that into the proposal because I was asking for money to continue building the library. And I thought maybe if I told them that I'd already written most of it, they wouldn't be interested in funding it, frankly. But that was cited as a main weakness. I'm looking for funding to basically make this an open source project and increase the community. My experience is that if open source projects are not well publicized, well maintained, and there's not a lot of engagement, people are reticent to use them because nobody wants a dependency that's dead after 2 years. So I figured I would ask for funding before I really took it open source and public. Does that answer your question, Jack?
Yes. You know, there are a lot of missions that are basing their Science Operations Center on Python now. Hermes and Punch come to mind. So I kind of wonder what they're doing for this decommutation stuff. But anyway.
Reiner Friedel is trying to organize this in headquarters to get everybody involved.
Oh, he is? Okay.
Just kind of a push. Yeah, Reiner's looking at maybe a push to, can we develop generic SOC components community wide? And so this would be absolutely something for that.
Yeah, I completely agree.
Oh, I mean, that's great. So maybe we can talk about opportunities to submit another proposal. I mean, I have, like I said, I already submitted one proposal, so I have most of the content already prepared. You need to make a new budget and figure out the scope, but yeah, I would be very interested in that.
Yeah, just watch out for the HDEE related stuff in next year, I guess. That's, I mean, and or communications from Reiner in the meantime.
HTM, I think is the,
Heliophysics tools and methods.
Okay, I'm gonna lean on Julie probably for a lot of that. Is that okay, Julie? Like,
Yeah,
you know what all those acronyms mean? I'm not super plugged
Yes.
into the heliophysics.
Yeah. I'll email you offline about all this.
Okay, sounds good.
Oh, thanks, Gavin.
Thank you.
Yeah, let's see. So next up, we have a Skywinder update from Bjorn.
Yep. Hello. Here, let me share my screen. Yeah, so this is just an update pretty much over the last 6 months of the Skywinder project. It's been a pretty eventful 6 months. So I'll basically talk just a little bit about the objectives of our project, and then I'm going to give the update. I won't bury that lead, and then I'll talk more about the project, what we've actually accomplished with the project and what it can be used for. And of course, hop in with questions at any time. There we go. So I just wanted to post our contact information. Biff Williams is the PI, and then I'm a postdoc at ASU right now. And yeah, here's our contact information. I also wanted to note that we will be presenting a poster at the AGU fall meeting. I really enjoy talking to people at poster sessions. It seems like the kind of the whole point. So I'd love it if you stop by and if you want to chat about this informally. So just broadly speaking, the objective of Skywinder for people who are new to this, who haven't heard, is that we basically wanted to make a Python software package broadly applicable to mobile aeronomy experiments. We're adapting code that was used for the PMC Turbo balloon launch that was used for the piggyback, and basically wanted to standardize it, make it broadly usable to people who aren't in our group. This also includes some analysis software that we think tends to be pretty useful in general, and then distribute it through the PyHC effort. So what have we done in the last 6 months? The first big thing is that this software has actually been used on another experiment. It's already flown twice for PMC Turbo and the piggyback, but we implemented this software on the Balboa experiment. This is a daytime auroral viewing experiment. They did a test flight in New Mexico, and it launched in September. And now they're preparing for an Antarctic launch. This was also good because it gave it was a good stress test of our software and made sure that all our features were useful and easy to implement. We also, this is a software accessibility update, but for a long time, this software has been, we've still been adapting it and we haven't made it public yet. It is now public. It's on GitHub. It's on PyPy, and it's on the PyHC site. And as you can see, we still have some work to do, especially regarding documentation. And the analysis software also needs more development, especially in the testing. This because the flight software, well, the consequences of that software failing were much larger. So we have done much more work on developing rigorous tests for it. I also wanted to plug a lot of the data from the PMC Turbo experiment has been hosted on the SPDF, the Space Physics Data Facility. So we basically have both the data from our experiment that's now public or is continuing to be loaded in public, while the analysis software is also public for any potential analysis collaboration. So let me just check the chat. Oh, perfect. So just to kind of dig in what this project is all about. Basically, we wrote a bunch of flight software to make sure that we can as autonomously as possible run balloon-borne experiments while simultaneously behaving well when we lose communication. Balloon-borne experiments and a lot of mobile experiments, they communicate via satellite constellation. Communication channels are not always reliable, but when the communication is there, we want to get as much data down to the ground as possible, and want to be able to actually operate, make hardware changes such as aperture, exposure time. We want to be able to review the data, and so we designed what we call is just distributed flight control software. Basically, we have a bunch of instruments, each of which can assume flight control duties. This is kind of different from the typical, balloon-borne paradigm where you have a lot of instruments, but you have one or maybe two flight control computers that are in charge of all telemetry duties. So we think this is broadly useful to a lot of future experiments that include, computers that are fairly powerful to deal with large data throughputs. We also hope that this will be useful, for example, for remote ground-based experiments. Maybe if you just want to set up an instrument somewhere near the Arctic or Antarctic, you don't want to have people monitoring it all the time. And you want to run it as much as possible. We divided the software up into a few key functions. And so basically we have something called the communicator, which communicates between our subsystems. We have many locally networked computers, each of which are running a communicator. One of those communicators is assigned leader duty, which means that it is the aggregator for housekeeping data, and it actually responds to most telemetry requests. This leader can be reassigned at any point. And in fact, all these systems actually receive commands. It's just ones that are not assigned leader duties are ignore most of them, except for the reassignment of the leader command, because they all need to register that. We also have software that operates on the ground, that receives the downlink packets, and it reassembles and tracks files. It also displays all this in convenient GUIs for human monitors. Those two bits are probably the most broadly useful, since experiments with distinct science objectives will be communicating over the same telemetry channels and will have a lot of the same telemetry needs, which is why I've bolded these. In fact, that's what we mostly implemented on the Balboa experiment, was the communicator and the ground control. We also have a pipeline which is more specific to our own hardware, which is just optical cameras. And most experiment groups will likely need to write their own version of the pipeline. And the controller is a bit of a go-between. For us, we had a lot of multi-step commands. You want to be able to send one command, but have the software interpret that command into many steps and implement them. For example, we often do a focus sweep to identify the correct focus. We want to send one focus sweep command with some parameters in it, and then the controller breaks that down into changing the focus by 2 steps on our stepper motor. 2 steps on our stepper motor, take an image, downlink the image, or downlink a part of the image, repeat for each focus step. We included the controller and pipeline, even though these are a bit more specific, because I think they will act as a good model for how to integrate specific experiment needs with these more generalized communicator and ground control software bits. Okay. And this is a model of our own experiment. We had 7 of these pressure vessels, which contained our science experiment and the computer running that science experiment. You each of those computers is running a communicator, a controller, and a pipeline subprocess. And then we networked it all together according to this diagram. I guess we tried to be very redundant in our networking, which is why we used several Ethernet switches and split the pressure vessels between them and split the telemetry channels between the two Ethernet switches so that we could reduce single points of failure. So here's PMC Turbo. There's me in the neon helmet. And this is shortly before launch from Sweden 2018. It flew from Swedish Arctic to just south of the Canadian, just south of the Northwest Passage in the Canadian Arctic over about 6 days. And we captured 6 million images during this time. Here's an example of our ground software as we were, this is actually a still from a screenshot from our software during the experiment. We were able to get data which has not been processed. There's no real background subtraction or anything, but we were able to get that along with lots of metadata. So we were able to note when scientifically interesting events were occurring in the sky, which we were happy about. Well, both because there was useful science happening that we were recording, and because our instruments, we were able to monitor and verify that they were working correctly. It landed surprisingly upright. And then we also flew a piggyback in Antarctica. This is the Super Tiger experiment, which was designed to measure gamma rays, but they gave us 60 watts and I think 10 megabits per second when we were able to bolt on one of our cameras, and it ran the same flight software and operated during the duration of that flight, which was about 30 days, and circled Antarctica twice. So my main takeaway here is that this software has been flight tested now once by a full-fledged science experiment, once by a piggyback science experiment, and now as well once on a test flight on a separate science experiment, Balboa, rather than PMC Turbo. So we're kind of slowly developing some, I guess, flight heritage for this software. We also include some just basic analysis functions that we think will be broadly useful. Flat fielding and time varying reflection removal, we believe, will be useful for pretty much any imaging analysis that doesn't already have perfect optics. So every imaging analysis. We have star identification and pointing reconstruction. This is just for rectilinear projection. And then we have some basic, power spectra, some feature tracking and movie making. So you can, as a human, go through your data quickly. So here's just an example of this data reduction. On the left, we have the raw data from an image. On the right, we have basically after flat fielding and time varying reflection removal. You can see it greatly improves our signal to noise. And then we're able to look through the image, identify stars, and then we actually just put that into astrometry, which is an off-the-shelf pointing star catalog and pointing software. And then we can use those coordinates to project into, geometrically accurate coordinates. So we know that the morphology is correct. So this is the same data as here, just projected onto the plane of the sky as we look upward. And this is essentially what our final data product looks like when we also threw it through the movie maker. So we're able to very quickly see what's happening on the sky. So I hope that was a good overview of basically what our software does and what we've done over the last 6 months. Are there any questions?
If you happen to think of a question later, also feel free to throw it in the chat.
Yeah, and feel free to stop by the poster.
Awesome. Looking forward to it. Thank you.
Thanks.
So next up, we're kind of moving from package overviews and intros into, more larger initiative type works. And first up, we have a MOS overview from Kyle.
Hello, everyone. I think you should be able to see the slides okay.
Yep.
All right, excellent. So I'm gonna talk about something that a group of us from Goddard started, the Magnetosphere online seminar series. So it's run by myself and largely David Sybeck. And then for the last 2 years since we've been running, we've had various help for moderating and running the seminar series. Jason Schuster did a whole bunch of work for us, Marco Severia, Homi Narion, and Ramya Banyu. So today I'm just going to talk a little bit about what the seminar series is, what it came from, and kind of where we're moving forward. So the Magnetosphere Online Seminar Series started at the beginning of COVID, almost just a month after everyone started to work from home. And it was started in order to help keep the Magnetosphere community active and engaged and seeing each other through COVID. We never anticipated that it would last as long as it did. And given how well it's done, we've continued it and hope to continue it on to the future. Our seminars are held weekly via Zoom at noon Eastern, which is a pretty good time. It allows most people across North America to attend and is still pretty good for the UK as well as getting into Asia as well. But it does tend to span a number of hours once you start including all those time zones. So we also stream and archive the seminar on YouTube, which has been much more popular than I ever anticipated it would. And I'll talk a little bit about that in the next few slides. So when we initially started, we didn't think that we would be going on for almost 2.5 years. So we initially started as kind of a set of overview and review talks of the magnetosphere and magnetosphere solar wind coupling. There was a recently published book, actually it's just been published, but it was in the works for quite a while, Magnetospheres in the Solar System. And we initially used this book to kind of help us step through the magnetosphere and identify an initial set of review topics. So we initially started with solar wind and energy input and talked about the dayside magnetopause, the cusp, and the field line currents, and the pole or the open field line region of the magnetosphere, then the night side, and then into the inner magnetosphere. That initially took us about 8 or 9 months. And from there, we've now continued on to a series of additional themes. We had 5 new themes following our initial run through of the magnetosphere. We talked about global simulations and ran through the more popular or larger global simulations, especially those that are on the CCMC, the Community Coordinated Modeling Center. We talked about, we had review talks about instruments in heliophysics, which was developed in order to give especially younger early career researchers an idea of how the instruments that they might be utilizing data from every day, how they worked. We talked a little bit about analysis in space physics and specifically data assimilation and machine learning. We moved on to talking about space weather, capabilities that we have at NOAA and also at the Met Office in the UK, and different metrics that we're starting to use, as well as new analysis methods in space weather, such as ensemble modeling, which is kind of a growing theme and growing activity within heliophysics in general. And then we moved on to waves, mostly because I enjoy waves, and talked about waves and wave particle interactions within the magnetosphere. Right now, we've started to focus on 3 topics. We focus on research highlights, so new research that has come out in the field. early career research. So the first Monday of every month, we have 2 early career researchers give seminars on their latest work. We actually have one going on right now. Francis Staples and Kazi Al-Shahid are talking today. And then we've started to do Python tutorials, which were the 3rd Monday of every month. With the Python tutorials, we initially started with Python in general to try and introduce the magnetospheric community to Python. This is the Python Heliophysics conference. And while Python is quite popular, I think, in the solar community right now, it's still kind of gaining traction within the magnetosphere community. And so the tutorials were meant to help the magnetospheric community kind of bridge that gap and start moving more towards Python. So in terms of our audience, we do meet every Monday. We have a mailing list of about 800 members at the moment. We meet via Zoom, and we usually get about 30 to 50 participants. And then we also stream it on YouTube. And on YouTube, we get about 5 to 20 people streaming the event. Largely, the number of people on the YouTube who are streaming it kind of depends on the age of who is presenting. The younger the presenter, the more YouTube people we have watching it. And generally, the older the presenter, the more people we have on Zoom. We also archive all the videos on the YouTube channel. And this is where the Magnetospheric Seminar Series has expanded much more than I ever thought it would. On the YouTube channel, by the end of the week, most of our videos or seminars have over 100 views. And so if you kind of think of that in context of GEM, the Magnetospheric Conference, or CEDAR, or even AGU, usually by the end of the week, we have more views than about 1/3 of the attendees at these conferences. And we have more views than people that would generally attend an AGU session. So it tends to be quite popular. In terms of YouTube, we have just broken 1,000 subscribers on our YouTube channel. And we get roughly, oh, that's not 500, it's about 1,500 to 1,800 views a month. So we get a large number of views. And we get somewhere between 180 and 240 watched hours, which is much, much larger than I ever thought it would be. And we also have international participation. So the nice thing about YouTube and the archive is that people are able to watch the seminars at a later date. And we generally get participation from just over 30 countries. The other nice thing about having it archived and on YouTube is that the seminars can be used as a teaching resource. And then there are a number of universities, specifically in the States, that are using some of the seminars as a teaching resource for magnetospheric and plasma courses. For our video, the most watched video we have just has nearly 3,000 views already. So they tend to be quite popular, and the YouTube channel has really opened up these seminars in order to make them more accessible to the community. In the future, we tend to, or we're going to continue with our initial, or what we're doing right now for our theme. We're going to continue with research highlights and continue with the focus on early career researchers. And then we're also going to continue with Python and heliophysics. In particular, Julie is actually going to be talking about the Heliophysics Summer School at the end of the month. And then going into the new year, we're going to start looking at Python packages in heliophysics and solar physics and giving tutorials on those in at least once a month. There's the new Snakes on a Spaceship, Frontier Special Issue, and we'll initially jump into those repos and those sets of code in order to do Python tutorials. And then I'm hoping to look at the Python Summer School and start looking at those main packages. The one downside to the main packages that were covered by the Summer School is that they generally take much more time to go over, but I'm hoping that we'll be able to get succinct 1-hour lecture that we can then point to the YouTube channel that the Python Heliophysics Summer School has. So we do meet once a week, and one of the biggest things moving forward right now is continuing to find speakers and continuing to find new themes. If you have any interest or you want to see any speakers coming up in the seminar series, I do really want to encourage you to contact us. One of the things that I've also found surprising is while a lot of people enjoy the seminars, we do get very little contact from people about what they might, about topics they might want to see or speakers that they might want to hear from. If you are interested in the seminars, I do encourage you to join the mailing list. It's a short email every Sunday night, just highlighting the next speakers and just identifying where you can see the latest stream. And you can also have a look at our current schedule and our past speakers. So we have just over 130 talks at the moment on the seminar series. So I do see there might be something in the chat, but that's still regarded to the last one. For those, if you guys have any questions, I know I've gone fast, but while the seminar series is really popular, it is quite quick. I can talk about it quite quick, but I am really open to themes and speakers that people might want to hear from.
Thanks so much for going over that, Kyle. Yeah, my talk is in 2 weeks, as I recall. So excited to come on your seminar series and talk about that. It looks like Rebecca from the Komodo project mentioned once if you can remind me what SWMF stands for. Rebecca is functional
Solar wind modeling framework.
Yeah, there you go. Maybe able to do a tutorial for you. So
yes, yeah. So things like Komodo, I think, would be really advantageous, especially things linking to the global simulations. I think the community could really benefit from that, and just from seeing tutorials on how to access that data.
Sure.
SpaceBuy is definitely on the list. Again, that's one of the larger packages. So with those larger packages, we will have to work with people to try and get them into an hour seminar. But I think that's something that we can point to the Heliophysics Summer School, because I know they have a full afternoon of YouTube resources or the recorded seminars from that school. So.
Awesome. Well, you've got some more chatter in the chat about potential seminar stuff. For now, thank you, Kyle. And let's move on to the next project initiative overview. So we have Xing on today to talk about space, which we've heard about a bit in the past, but it's been a while since we brought it up at one of our meetings. Xing, I think you're muted.
Okay, can you hear?
Yeah.
Okay, so I've been asked to give an overview of space. Of course, this is not just my talk. Let me go back. If I can go back. I can't go back. There you go. Okay, so overview of space. So I've been asked to give this presentation, and of course, none of this would work without the working of the space group. At any rate, just to bring everybody on the same page, SPACE stands for Space Physics Archive, Search, and Extract. It is just a metadata model designed for describing heliophysics and space weather resources. So it's especially designed for describing the resources for this community, for the heliophysics community. And it was actually developed over 20 years ago by the Space Consortium. At the time, there's a group of people working in the trenches, and they discovered that they have data from different places, and they were all described in different ways. So what wouldn't be better to have all the description of the data set to be uniformized so that everybody can use it. So back in the late 1990s, there's this initiative to develop this space metadata model. And over the years, there have been major and minor releases of the space metadata model. The first release was back in 2005. That's the first version. The latest version is 2.5.0, just got released back in late September. So as you can see that there are a good number of releases already, and there are major and minor releases depending on the significance of the changes. So over the years, more and more people are adopting the space metadata model. And back in 2001, the COSPAR panel on space weather actually recommended that space as a metadata standards to be used for describing heliophysics and space weather resources for COSPAR. And actually, HAPI mentioned earlier, is also the other standard for access protocol. So there were two standards recommended back in 2021 by COSPAR. Earlier this year, the NASA Heliophysics Division also issued its latest heliophysics data policy, and it's actually stipulated that space is required to be used by all NASA-sponsored missions and projects. So over the years, there are now, my last count is about 13 major heliophysics data archives and services worldwide that have adopted the space metadata model. And currently, the space metadata model is being maintained and further developed by what is called the Space Group, which is really just a smaller set of people who were involved in the original space consortium. And this space group now is predominantly NASA-led. And this group here, it's open to anyone who's interested. And it really has the responsibility to maintain and develop the space model. And the group meets bi-weekly, and the announcement comes out on this particular email address. So if you're interested in joining, you can subscribe to the space group mailing list. Let's see if I can remove this. Okay. I don't know if this is actually distracting or not. Okay, back in 2016, NASA has established the Space Metadata Working Team, the SMWT, and this group here worked in tandem with the Space Group. So the SMWT primary goal is to implement the space model and provide assistance to the community in creating space metadata model documents. This group also meets every other week and is exactly out of phase with the Space Group. So we actually have a space-related meeting every week on a Thursday. Every other week is the Space Group. The other every other week is the SMWT. And since the SMWT has the charter to implement the space metadata model, so invariably they will also find issues in the implementation. So they will provide the issues back to the Space Group for resolution or further development if needed. So the SMWT now also manages the space metadata registry. Okay, here is an overview of the space ontology diagram. So when we talk about heliophysics resources, there are different types of resources. There are 4 categories of resources, and they're color-coded. The green boxes indicate the resources that originate the data or the product. So you would have instrument, observatory, and the authors or the data set creator. So these are the origination. The boxes in the blue are the product themselves. The ones in yellow is the simulation extension. So this is where all the simulation models, model products, and simulation runs are being described. And the last one is what we call the infrastructure that includes data repositories, services, registry, and software. And each category of resources, they have different resource types. So you can see each of those smaller boxes represent one of the resource type under each of the resource category. So let's take a high level view of what the resource description is identifying. So every resource could be a data model or a piece of software, Python code, if you will, is going to be identified by a unique space resource ID. So the resource ID has the following form. Space is just the namespace, naming authority, the resource type, so you can identify what type of resource this is, data, model, or what have you, project, observatory, and so forth. So the naming authority is the first tag in the resource ID, so that is a convenient way for us to track the resources. And the naming authority is now typically assigned to the organization that commissioned or sponsored the resource. So you can think of it as just the funding agency. So if it's a NASA mission, then the naming authority would be NASA. If it's an ESA mission, then it would be, the naming authority would be ESA, and so on and so forth. It could also be assigned to a long-term major project like the CCMC, Ayuganak, Gong, Madrigal. So these are long-term major projects that oversees a lot of different types of resources within that organization. So you can use that as a naming authority. If none of these works, you can default down to the PI institution. So the PI is ultimately responsible for creating that resource. So if you cannot identify the funding agency, because in a lot of cases, you actually have multiple funding agencies for a given resource, then you will use the PI institution as the naming authority. So with the naming authority, then we can define the space registry, which is then the collection of space metadata under different repositories identified by the naming authority. So right now, the space registry is hosted in GitHub. So every new naming authority have the authority of their own metadata resource will have the managing capability of their own resources and so forth. So each naming authority or its designated representative. So even though NASA might be the naming authority for the NASA resources, but the entity that actually does the editing or managing the resource could be down at the SMWT level, for example. Here is a graphical view of the schema of a resource description. Now, space is just a information model, so that means that it provides a tree structure for how every resource is described. So in this example, it's for numerical data, is split up into various types of description field that you have to fill in, and then you can see how the description structure moves on down at every level of details. There are required information and there are optional informations. So required information means that those are the minimal set of information you have to have in the space document in order to fully define a resource ID. And the space model provide description down to the parameter level. So on the lower right-hand side, you can see that the parameter level would have field quantity, particle quantity, wave quantity, or mixed quantities. So these are primarily relevant to heliophysics observations. Here is an example of a space document. The one on the left is the original XML file for the space document. The one on the right is human readable web page rendering of the space document. And you can see that I have annotated the required resource information. You have the resource ID, the resource header, access information. This is the information that tells you how to access the data or the resource. And further down the document, you can see the measurement type. So those are the required information that you have to have in a space document. So how do you create a space document? If you had a resource that you need to describe, there are actually different ways to do the space documentation. We have developed a web-based editor for you just to fill in. So if you didn't know anything about the space schema itself, the space editor is an implementation of the space schema. So all you need to do is to fill out the various text boxes, if you will, or the information that's required. And then you move on, and then you can save that document out as an XML file. So you have two versions, one for observational data and another editor for model data or the simulation models. If you have a lot of data that is CDF or NetCDF based product, so we actually have an adapt tool that developed by Reba Gartzi. And what it does is that because of these, what is called the self-documenting and self-describing data format, those data format already has data or metadata embedded in the data file. So the adapt tool simply just goes in the data file and extract the metadata and put them in the right places in the space document. More recently, DOIs are also minted for dataset under NASA naming authority in particular. Other naming authorities like ESA, they're also creating DOIs. So what we now do is actually, if and when a resource has a DOI minted, we would put the DOIs back into the space document to make it more complete. So the minted DOI are then added back to the space description. So to create a DOI URL. The DOI URL plus the access timestamp then becomes the persistent data reference. So down here at the bottom is an example of a reference to a data set. So this is the language people now use in their references in the paper or bibliography. So this access time is important, as I indicate next. So this is a partial view of a completed space document. So you start with the title. This is the same DOI reference that I showed before. And at the back, here is the access timestamp. So when you open up the landing page, the system will generate a time at which you access this particular time, this particular web page. And if you compare the access time and the revision history of the metadata, that actually tells you which version of the data you're actually using or referencing. At the upper left-hand corner is the data access points. The data access points is actually extracted out from the access information from within the space document. But this here it gives you a summary, a handy way for you to access those different protocols where you can access the data. So it is one of these, for example, happy is listed here. So if you're accessing the data using Happy, then you know that you can actually use that protocol to access the data. Okay. FAIR. The FAIR principle has been very popular discussion topic in informatics. And space is fair. It is compliant with the FAIR principle. FAIR stands for findability, accessibility, interoperability, and reusability. Findability, of course, we have resource ID. Every resource is uniquely identified by a resource ID. So if by the resource ID, you can find that data product. Access information in the space resource description allows ones to access the data. So it actually contains things like repository ID that tells you where the data is located and the specific access protocol one can use to access that resource. The schema and data dictionary provide a structure and standards that enable uniform resource descriptions. So if you have a service that is that can read a space document, then that means that every resource that reading the same space schema and using the same data dictionary can access that resource. Reusability. This is also important because even though parameter description currently is optional, we strongly recommend that the data provider actually describe the parameter. For example, Happy relies on knowledge of the parameter to get the information to actually get the parameter you want. So description of the parameters are important. And with DOIs and the data referencing, it's also allow people to track how data has been used and in what applications. This is the home page for the space group. You can access the data model through the very top link on the space page. If you have questions or comments, suggestions, you can send email to this address. The official current release of the model is always now announced on the top page. So you will always know what is the latest version of the space metadata model. So here is just a few key references to space. Of course, we have the space documentation, which is available online on the space website. The definitive reference for space, if you just want to reference the space model, this is the paper that we published several years ago by Aaron Roberts et al. In Space Weather. And there is a new publication, hopefully coming out. It's been submitted to the Advances in Space Research as a special contribution to the COSPAR iSpot exercise. And this paper is now currently under review. Hopefully it will get accepted soon. With that, I think that's all I have.
Wonderful. Thanks for the overview, Shing. It looks like Ryan had a question. Is there a place in space for connecting DOIs, i.e. a paper with the data set that it uses /sites? How would one do that with space?
I'm not sure if I understand the question.
I can answer it if you like.
Yeah, go ahead.
Okay. The DOIs are assigned to each product, and DOIs are also assigned papers in a natural way from the publishers. There isn't quite the direct link that I think you'd like, Ryan, but there is. You can have a information resource associated with a data set. That information resource will have the DOI associated with it. And there won't be, and in principle, if the paper has been published properly and everything's up to date, it would use the DOI from from the data products that it's using. So there are connections. I'm not sure it's quite the connection you would like, where you just say you click on a resource and then it would allow you to click on all the papers that cite that. I think that's something that the ADS is working on at this point. So it's coming, but it's not there yet.
Yeah, I think the real answer is what we need to do is for the people who are writing the paper actually cite the DOI for the data sets they use to support the paper. That would make it easier.
Well, that's the essential thing. Once you do
Right.
that, then you can begin to search. You can search ADS for that DOI even, and
Right.
it would tell you what things have used it.
Awesome. Well,
So
there's
Ryan, I'm not sure if we answered your question, but if you want more info, we can talk more.
Yeah, thank you, Shane. Thank you, Aaron. I appreciate that.
and Shing/Aaron, it looks like there's some more comments, questions in the chat, but we should move on to our last presentation of the day, which actually is from Ryan talking about the TOPS initiative.
Great. Thanks so much, Julie. And I know we're running a little bit short on time, so I will try to be brief. And I hope that you're able to see my slides okay now.
Yep.
Okay, great. Thanks for all the talks this morning. A lot to follow up on and think about. So thank you so much. And thanks, Julie and Sean and others for organizing today. These were always such engaging meetings. So I'd like to bring the open science perspective to this meeting. And I think really where I'd like to just take this just as a high level is to present the opportunity that open science and some of the initiatives that are going on around it for this community, because I think we're well positioned to kind of be leaders within some of those initiatives. I'll speak specifically within the NASA Transformation Open Science Initiative, or TOPS. And just to note that has the NASA name on it, but it really is a broad across industry, academia, any community, but also outside of the borders of the United States as well. So it really is a broad movement that all are welcome to and encouraged to participate in. I'm going to try and relate that to heliophysics a little bit and give a clarifying definition of what how we are kind of thinking about open science, describe a little bit of what the existing ecosystem is within heliophysics, which will certainly involve a lot of the efforts that are involved in this room and that people represent in this room. And then talk just a little bit about some opportunity trying to inspire you to join the TOPS community forums, to get more involved and become more aware of some of the things that are going on there. So some of you who have heard me talk about this before will recognize this definition, but it's one that I think encapsulates a lot of what we're thinking about with open science. It's from this paper that I've linked there, and I'll provide these slides afterwards. But it talks about open science as transparent and accessible knowledge that's shared and developed through collaborative networks. And I like this because it has kind of two pillars to it. There's the intelligent and accessible data infrastructure and platform that is required to use it. This first element of the definition. And the second one is really centers the participatory ecosystem that is required for open science and actually sharing and governing the knowledge that we have. And so I think it makes it clear that open science is not just a technological initiative, but very much a cultural one too, which I'm really happy to hear has been on such display this morning with things like Kyle's Moss. That's really a cultural thing to try to introduce people to and socialize concepts and ideas, as well as these meetings as well. So I'm going to talk about TOPS itself to give you a little introduction. If you haven't, you'll see a number of places in this presentation where you can grab a QR code and get some more information. I'm really trying to help direct you to that personal discovery. But you see the people that are involved in kind of the core team of NASA TOPS here. But it's addressing a number of different things, but it's really trying to transform how we do science at NASA and more broadly to be more open. And what we mean by that and kind of where we're placing focus is accessibility, reproducibility, and inclusivity. So this can have a number of reaches within the scientific community, including research that's cited more, has a bigger impact, and is more transparent and allows and invites others more people to contribute to it. And it's very inclusive. It can be productive and is the way to approach collaborative projects, provides more access to more people to quote unquote hidden knowledge. And you can kind of see a couple of the different dimensions that we think about these three pillars of open science. I'll mention one thing that's very much a large focus right now, which is called the open science curricula. So this is kind of to increase literacy and capacity for open science within the community. And the way we've been thinking about this and designing this curricula is across 5 modules, beginning with the ethos of open science, which is what is open science? What is the philosophy of it? How do you understand what open science is before you get into some of the concrete technological and technical aspects of it, which include these other 4 modules, which span across open tools and resources, open software, open data, and open results. These are provided and described in more detail on the TOPS GitHub page. And so I'll encourage you to dive deeper in each of those there and really contribute to shaping what those become. I really would like to see heavy heliophysics participation in shaping these. There's a solicitation out in NASA Roses that I'll talk about in just a moment, but it's inviting the community to help design what these look like for discipline-specific development. So I would love to see us develop a really strong, robust heliophysics open science curriculum. And I think it begins in places like this Python heliophysics community. So I want to bring it to heliophysics and acknowledge, and I always like to point out that we have a long history of doing what is now being talked about as open science research within heliophysics. I don't need to belabor these points here, but I just do like to acknowledge the wonderful work that's been done with the SPACE model. I'm so glad that Xing was able to give a presentation this morning. The Community Coordinated Modeling Center, so you heard from Rebecca, and then also this International Heliophysics Data Environment Alliance idea, showing that heliophysics has kind of this global international component to making data, making knowledge more available and open. And so these are elements of what I would consider the heliophysics open science ecosystem right now. And so we do have a strong legacy. I think we're one of the science mission directorates within NASA that enjoys kind of having thought progressively about what open science might be for us, even though we may not have been calling that before. But I do want to take a tour around and talk about some of the existing efforts that I like to raise and draw attention to that I think fall under this banner of open science within heliophysics. So I've organized it around these modules of open science in the curricula that I mentioned before. But in terms of the ethos of open science, this is about building community literacy and capacity. So we have our NASA Center for Helioanalytics, which I hope is not news or new to most people in this room. But if it is, take a look at the website or talk to me. This is a growing kind of community that is trying to help our groups do more robust and responsible data science, to do more scientific discovery with those new tools that are becoming available. We have a town hall that I'll draw attention to at HU. This year, it's actually at the very outset of the meeting. I'm really excited about that. It's kind of centering some of these conversations about what is the open science component of the Center for Helioanalytics. We would love to have you join us there. That's going to be very much discussion oriented, and we hope will set the tone for the rest of the week at the HU conference. That will be available both online and in person. In terms of some other aspects of the ethos of open science, there's a lot of community workshops going on around different aspects of this. So last year, Brian Thomas held one that was oriented around understanding heliophysics infrastructure and the next generation of that. And I think that's led to a lot of how we're thinking about that now and what you're seeing being reflected in the Heliophysics Digital Resource Library. So that's exciting. We have some resources, some workshops going on around how do we build knowledge infrastructure for heliophysics? So how do you start to help improve how we relate our data, our information, and the way that we describe our knowledge within heliophysics to make it more accessible and usable. Part of that is this glossary harmonization activity, which is trying to bring together and make interoperable the 10s, 20s of glossaries that we have available that are being used to describe heliophysics data and knowledge. So that's another thing that is going on. There are a lot of living conversations going on. So we have kind of this GitHub forum where people contribute thoughts about data science. And I welcome you to join there, kind of read, get involved, and add your thoughts as well. And then there's a new space collection that we have on this open access PubPub platform that's curated by by MIT. And we created a special section with that for our community to talk. We called it the Space Commons. And there's a number of different elements to that. There's actually a very clear article for how you might contribute. This could be anything from something like a blog post, very short form, that is trying to inspire discussion, to longer form if you have something else to say. But we welcome all contributions there. So please take a look and make your contributions. I know this community has a lot to contribute. And then, of course, there's Helionauts. I think everyone in this community is well versed with this, so I'll kind of not go deep into this, but it's a wonderful resource. Raphael Attier has done a fantastic job with that. And then there's a lot of visions taking place for how this is growing, how open science is growing. One thing that a number of us in this community have written is called the need for a space data knowledge commons. And I'd love for you to take a look at that publication. And then Rebecca Ringet has led two excellent efforts called the Diaries Ecosystem and the Liked Resource, which are both published articles now and outline a lot of some of the aspects of this thinking as well. In terms of the tools of open science, obviously this is going to be high level and just a glimpse. I'm not claiming for this to be comprehensive, but I just wanted to mention a few. This is about cultivating know-how for open data software and results. We held a Jack Eddy Open Science Symposium earlier this year that collaborated with 2i2c on spinning up a Jupyter Hub instance for this workshop at the symposium, because it was going to be organized around having working groups for grand challenges that required open science to be solved. And that was really successful, and I was really excited about that. And those collaborations have kind of continued to go in the months between. Then there's this idea of an open knowledge network. So growing the availability, the accessibility of our knowledge and linking that using some mature semantic resources. So maybe something like SPACE provides structure to the data so that can be accessed. If we were to be able to create ontologies that structure our data and our information or our knowledge, we can better link them, have better accessibility to them, use some of the data that we may not be aware of just by searching or the previous knowledge, the a priori knowledge that we have. So a couple of efforts that I've been working on are the Convergence Hub for the Exploration of Space Science. This is funded through the National Science Foundation. And this was trying to develop a space weather ontology that connected everything from the sun to society. We focused specifically on the power grid for that instance, but that the development for that is sufficiently general that it could be applied to other circumstances as well. And then there's one that's kind of focusing on heliophysics more generally, which is the Heliophysics Knowledge Network. And so both of those have resources that you can take a look at. In terms of open data, one that I think is a clear example of excellent use and creation of open data has been the Solar Dynamics Observatory. Not only does it provide the data in excellent formats, but also it fosters the use of those data. There's been a nice ecosystem of software development around that. And so I think that's an example I draw attention to. Additionally, I think the Super Magnetometer Initiative is one that's excellent. This is representing over 200 distributed ground-based magnetometer data sets provided by different groups and collected, and it's standardized in a lot of ways and brought together in this really useful resource. And I know that you heard John and them talk about making access to this available through something like Happy, which I'm excited to see. And then I think it's really important to draw attention to the fact that I think the leading group for open software in our community might be this Python heliophysics community. So again, props to everyone that's been involved in this. Julie and Sean, an excellent job with curating this community. And then obviously the Heliophysics Digital Resource Library represents a kind of culmination of a number of these things linking together. And we're certainly adding some of the knowledge infrastructure development that we've been doing into HDRL. And in another talk, I will happily share some of the resources, some of the ways that we've been trying to grow heliophysics representation within the ADS and make that part of HDRL's effort as well. But not today. And then I'll mention the cloud environment that a number of you are on and contributing to, but it's really an excellent example of bringing the community to be able to do analyses together. And so that's a great place to be focusing some of these efforts. And then finally, on the open results component, there's been efforts and discussions over the previous few years about the geosciences paper of the future, things that make executable papers and computable papers possible. Which I think has been kind of wonderfully advanced by Sean himself with this recent example of doing an executable paper within heliophysics. So I encourage people in this group who haven't had a chance to take a look at that paper to take a look at it, learn from it, and try and bring some of those ideas into the way that you publish your research. So kind of bring this back to TOPS. I think that it's an excellent opportunity to advance some of these pockets. You'll notice that these are really exciting, but there's also some gaps within the way that we're doing open science within heliophysics. And I think TOPS is an opportunity for us to fill some of those gaps in. The way that TOPS is moving forward is targeting 2023 as what they're calling the year of open science. And you can see some of the goals there, but this is really kind of the launching point for this upward trajectory of open science within NASA and more broadly. You can grab a couple of these QR codes here if you want to stay informed through the email list, and then just kind of browse around the TOPS website. I'm happy to talk with you offline about specifics of this, but I encourage you to look at the GitHub and take a look at the discussion forum there, which is very active, and there's some exciting things going on. There are a lot of opportunities for this community to get funding from TOPS and within the TOPS program, to do some of the work we've talked about being important at this meeting. And so I just wanted to point people to this. The big one that I think is out right now is this transformation to open science training, or TOPS-T. This is trying to support people to develop tutorials to showcase open science, maybe lead virtual cohorts to work through some of the virtual curricula, and or put together summer schools. So I know a number of people in this community already lead efforts like that, and this could be an excellent thing to advance that. Just to add a few more details about TOPS-T, it's very active now. There's a number of TOPS community forums that have been held to answer questions about this. I think the most recent was October 13th. I posted the link here if you want to review the video and the slides from that. There's an optional notice of intent due tomorrow. No, this is actually later this week, I guess on Thursday. And then the proposal will be due at the beginning of December. But this is there's a lot of resources for this. So I encourage people to take a look at that and talk to me if you're looking to get connected to other people that are potentially applying to that. And this is a little bit redundant, but this is just kind of highlighting the year of open science. This is going to be launched at AGU this year, so keep an eye out for a lot of the things that are going on there. Our town hall could be something that points you to a lot of the happenings at AGU, but I'm excited about that. And with that, I'm just going to kind of leave it there because I know we're coming to the end. But I will just leave up this slide that shows you a number of ways to get further involved with TOPS. Especially in with regard to co-developing year of open science activities. So thanks again, and I'm happy to take some questions.
Thanks, Brian. It looks like you have a couple questions in the chat from John for the open source learning modules. Is there a plan to train the trainers? If people from different institutions can get spun up as trainers, institutions could leverage these trainers to get their own science teams up to speed. This approach would work well at APL, for example.
Absolutely. Yeah, it's a great point. And I think train the trainers is language that has been used in a few of these calls already. I know TOPS-T, that would be very relevant to TOPS-T. So take a look at that, John. And then I'll try and dig up these other areas where that language has been used, but I know that train the trainers, that's very important.
Awesome. And then there was a question from Rebecca. Is there any date or location plan for the next year's Jack Eddy Open Science Symposium?
Good question. There is not yet. I think we will be meeting soon, maybe after AGU and things settle down from that a little bit to start working on that. But you can probably expect that to be later in the fall of next year, I would think, just because we haven't put a lot of that in forward motion yet.
Sounds good. Any other questions for Ryan? Not. We can go ahead and wrap up for the day. Thank you, Ryan, again for that excellent presentation, and to all who presented today, and to all who came and attended. We'll see you again tomorrow morning, same time, same place.